All right, one more and you're home free. This one's on hybrids. This one will be quick. We're going to focus here, because that is the aim when we think about hybrid functionals, on the exchange part of the exchange correlation energy. Generally, the exchange piece is about 10 times the correlation energy. So errors in EX have a big impact, and improvements to EX, in principle, should make things better. What we know is that exchange is fully non-local. And when you think about how you calculated wave function theory, you do an integral over the whole orbital in order to get the impact of exchange on that orbital. And that integral over the orbital in order to know an energy contribution, and so it makes it non-local. It's not like you just need to know the orbital here, you need to know it everywhere to get the contribution. Furthermore, if we were working purely in a density functional context, we know that the self-interaction error or the self-interaction correction requires exact exchange. You've got to remove the orbital you're concerned with, and local approximations don't do a good job in treating self-interaction. So when you look at that, you say, well, why not calculate it exactly as in Hartree-Fock? You get exact exchange. You just take the cone-sham orbitals and calculate the exchange terms as you would in Hartree-Fock. And we call that exact exchange, and we're going to use that in a little bit. But the problem is, you trade off another issue. The correlation functionals we have are all local. And now what you're doing is you have a fully non-local exchange piece and a local correlation piece, and they are unbalanced. And in particular, what they can't get right is something like H2 dissociate, because you get exchange completely right, you get correlation largely wrong, and that turns out to be an error. I'll fix that while we're there. Having said which, and I'll come back to it just a little bit, the thinking on this is changing. That is the use of fully exact exchange. I'll talk about it in a second. All right, so here's the most complicated part of the book, in my opinion, the adiabatic connection. The adiabatic connection is one of the funkiest things in the world. It basically is an integral between the cone-sham system, whose density is exactly the same if you had the exact exchange correlation function, as the true system. And what you're going to do is you're going to vary the electron-electron repulsion, but that also means varying external potential in order to connect these beasts. So you've got to vary the external potential in such a way that the density doesn't change. Okay, well, I don't know who thought that up, but that's what they did. Problem is we only know the two endpoints. We know the cone-sham non-interacting case, where EX is this exact exchange, the Hartree-Fock-like exchange. And we know the exact wave function, where it's exchange plus correlation. The idea is you're going to approximate this integral as a weighted sum of endpoints. So all you know is this one, in principle this one, and it could look like this, it could look like this, it could look like this. And you're going to, I mean this in the nicest possible ways, you're going to guess the form. So one thing, you know, if it were this, you'd say, well, it's sort of 50-50, this piece and this piece. And if it were, that is exact exchange and then fully wave function based. On the other hand, if it's here, you see it, you know, the slope's pretty much, so it's a little more weighted towards the fully interacting system. And here, it's even more fully weighted to the interacting system. So you might think this was 50-50, that this was, I don't know, 30-70, this might be 20-80. And so how are you going to get this? Well, you know, you might guess it, say it's a half exact exchange, non-interacting, and a half fully interacting. And people tried that, and it wasn't terribly accurate. Instead, what they did, and this is B3-Lib, was just fit to experimental data. These are atomization energies, although I'll check for next week. And what they found was that the right amount was about 20% exact exchange, 80% local density approximation. You see that here. A is the parameter that determines how much exact exchange there is versus how much local density approximation there is. B determines how much Beckett exchange there is, and C determines how much Li-Yang-Parr correlation there is versus the local density approximation. So it's really this weighting of how much of each of the terms is in there that you're going to use. Now there are lots of other options. I just showed you B3-LIP, but the PBE hybrid is about 25% exact exchange. Values mostly come, the weighting mostly comes from fits of experimental data. But Becca, you know, after 30 years of leading the way, he now says that the only thing you should do is use exact exchange, so we know that's the right answer. There hasn't been a lot of movement on that. It still seems that the hybrids, as they're constructed, are winning the day. And it's because the hybrids and the meta-hybrids are quite accurate. And so next week, in the last set of videos, I'm just going to try and introduce you to 4 of the functionals that are well known and that we're using. We're not going to go into nuts details, but I just want to think about the philosophy, how they came about, and what their successes are. So with that in mind, I'm going to call it quits.